Welcome to the video for Chapter 19. Today we're going to build on the work that we've previously done. You'll remember that we first derived Maxwell's equations, then we used Maxwell's equations to derive the wave equation, and today we're going to solve the wave equation. We're going to see that there are many solutions to the wave equation, but the one that we will be most interested in is the plane wave. And we'll talk about how plane waves propagate and the circumstances under which they're a solution to the wave equation. So we're going to talk in particular about waves moving to the right and waves moving to the left, or those moving in a positive direction versus those moving in a negative direction. We're going to explain what a plane wave is and under what condition it is a solution to the wave equation. We're going to calculate a variety of different quantities associated with plane waves. We're going to calculate the electric or magnetic field given the other for a plane wave in free space. And we're going to determine the magnitude and direction of energy flow for a plane wave. Well, our historical perspective for today seemed like a pretty easy choice. Guglielmo Marconi is known as the inventor of radio. He was an electrical engineer and an inventor. He spent his entire life studying radio wave transmissions, and as a reward for his work, he received the 1909 Nobel Prize in Physics for the development of what's called wireless telegraphy, which was their name for what we now call radio. So let's talk a little bit about general solutions to the wave equation. The most general solution to the wave equation, you'll remember that this was the wave equation that we learned about last time. The most general solution includes two terms. There's an f of z minus ct and a g of z plus ct. What we're going to find is that the f of z minus ct is moving toward the right, or in a positive direction, and the g of z plus ct is moving to the left, or in a negative direction. I'm about to prove that to you, but for right now, just be aware that the most general solution has a wave that's moving to the right and a wave that's moving toward the left. And they can interact with, actually, they don't interact with each other. They can pass through each other, and they remain unchanged by having interacted with, or by having passed through each other. So let's take a minute and consider what would happen when we say that a wave is moving to the right at a certain velocity. Well, you know, if you have a sine wave, and that sine wave is, quote, moving toward the right, then that means that you can look at any particular point on that sine wave, whichever point you'd like to choose, and you're going to see that it's moving at a constant velocity toward the right. Well, if that particular point it maintains its characteristic, then whatever that characteristic, whatever say the sine or the cosine, whatever that was, it's going to need to be constant. So, for example, this point would correspond to a sine of pi over 2, and this point would correspond to a sine of pi. Whatever that point is that we've chosen, it'll correspond to a particular value, and that value is going to remain constant. Now, as z and t both are changing, it's going to change in such a way that the wave is going to move. And so we'll see some more examples of this, but for what I want you to see right now is that if we look at this first term, f of z minus ct, that z minus ct term is going to need to be constant if we're talking about a particular point along that curve. And if we take that z minus ct as constant, we can take the derivative of both sides. Dz dt minus c times dt dt is just 1, and the derivative of a constant is always 0. So we find that dz dt minus c is equal to 0, or dz dt equals c. Now there's an implied plus sign there because that wave is moving toward the right, or it's moving toward positive values of z. And if we did a similar derivation of the z plus ct term, we would find that it was moving toward the left or moving toward negative values. It would have a negative c for its velocity. So we can see that this wave, this solution, this proposed solution, would have a rightward moving part and a leftward moving part, although we could omit one of them. You know, if we just said, nope, we're just going to have a right moving part, that would be just fine. That would be a solution to the wave equation as well. Or similarly, we could just have a leftward moving part, and then that would be a solution as well. But the superposition of them is the most general form of the solution. So let's prove that that function is the solution, or is a solution to the wave equation. What we're going to do is we're going to first of all take a couple of sort of interim or temporary variables, alpha equals z minus ct and beta equals z plus ct. These are going to help us as we're deriving the results because we won't have quite as much to write. So we can now rewrite e of zt as f of alpha plus g of beta. And then if we wanted to find the derivative of e with respect to, say, time, well, we can take the derivative of the f term plus the derivative of the g term, and we can use the chain rule to break this as the dependence of f upon alpha, so that we have the dependence of f on alpha multiplied by the dependence of alpha on t. And it is not precisely correct to say that you can cancel the alphas and see that there is in fact a partial of f with respect to t that remains, but it is a shortcut way of thinking about it. So it is a way of saying, oh yeah, I can see that this chain rule would in fact give me the quantity that I wanted, which is the partial of f with respect to t. And then similarly over here, we would have a partial of g with respect to t if we canceled the partials with respect to beta. But that's not precisely correct, so I'm going to erase those marks and just say that this is an application of the chain rule. Well, let's go back up here to the top. What is the partial of alpha with respect to t? Well, that's you'll see that there is a negative ct term here, so this is negative c. What is the partial of beta with respect to c, or with respect to t? That's a positive c. And so if I come down here, you can see that the partial of alpha with respect to t is negative c, partial of beta with respect to t is positive c, and that's what appears in equation 19.11. So I can then do a second derivative, and it basically follows exactly the same pattern, and that is going to give me a second power here of both the negative c and the positive c. Well, that's good news, because that means that that squared term is going to mean that the negative sign on negative c is going to go away. We'll see more on that in a second. But let's now take the first derivative with respect to z. We're going to apply the chain rule just as we did before. We're going to see that the partial of alpha, let me scroll back up here, partial of alpha with respect to z, so partial of alpha with respect to z is 1, because it's just z, and partial of beta with respect to z is just 1. So this derivative is going to be easier because this is going to become 1 and this is going to become 1. And so then you can see that we end up with the 1 multiplying each of them. Those will go away. But when we take the second derivative, we get a second 1. Doesn't really matter. 1 to the first power is still 1. And those can really be neglected. They can be omitted. Now what we're going to do is we're going to take equations 19.12, which was the second derivative with respect to time, and 19.16, which is the second derivative with respect to z. And we're going to plug those into the wave equation. So remember that this is the form of the wave equation, and that what we want to do is prove that that is equal to 0 in this case, because the wave equation requires that that be equal to 0. So I'm going to take my quantity here that represented the second partial with respect to z. Don't forget that there's a minus 1 over c squared term here, so that's where this minus 1 over c squared term comes from. and actually this is right here, so I can just point to there. And then this term was the second derivative with respect to time that we previously had derived. And then notice that the c squareds are going to cancel. And then we have a minus sign in here, which means that this term is going to cancel with this term, and this term is going to cancel with this term, and everything goes to 0. And so what we find is that when we do calculate the second derivatives with respect to time and space and plug them into the wave equation, we do in fact get the right-hand side to be 0, which therefore means that this is a solution to the wave equation. So, good. The most general possible solution to the wave equation, we see that it is a wave moving toward the right superimposed with a wave that's moving toward the left. So which of these functions is a solution to the one-dimensional wave equation? This is actually a really profound result, that we can have a rightward moving wave and a leftward moving wave, and that if we can ever figure out how to get an electromagnetic wave to propagate, it'll propagate forever. Which is why, again, when you look out into the night sky, you can see light coming from stars that has been traveling for years and years and years. So I can factor out a 4 out of these first two terms, z minus ct times 4, plus 5 times z plus ct, and I do in fact have some function of z minus ct plus another function of z plus ct, and so therefore, yes, this will in fact, I should probably write out the word yes instead of just a check mark. That will in fact satisfy the wave equation. Now here we can see that this would be 4 times z minus ct plus 5 times z plus 2ct. Well, that would require that the wave propagating toward the right would have a velocity of c, and a wave propagating toward the left would have a velocity of 2c, and that's not allowed. The propagation of both halves of the wave, or both parts of the wave, have to be equal to each other, so no, this one will not satisfy the wave equation. Then we can consider, what about the sine of k times z minus ct? Well, right away I can see that there is a z minus ct term here. There's no other occurrence of z or t, so yes, this is fine. This is a function of z minus ct. And then I can look at, this is a Gaussian curve, still a function of z minus ct, and yes, this will in fact satisfy the wave equation. Now this last term is interesting. I don't have a sum of z minus ct and z plus ct. I have the product of those two. And because it's a product, I can't separate them out. It's a combination of a rightward moving wave and a leftward moving wave, but it's not a superposition. And so therefore, no, they can't be separated. So no, not separable. So we can see that it is, there are many solutions that can be a solution to the wave equation, but not everything is a solution to the wave equation. In particular, the z minus ct and the z plus ct have to be separable, and they have to have the same velocity. And if either of those conditions are not met, then it will not be a correct solution. Okay, so that's the most general solution, but it's not the most useful solution. The most useful solution is a plane wave. And plane waves were very confusing to me when I was a student. I remember being confused by them and not understanding what was important about them. I'm going to do my very best to try to make it easy for you to understand. I've drawn a picture here using MATLAB to try to illustrate what's going on with the plane wave, and you can see that the plane wave is really only changing in one direction. It's only changing in the z direction. And so you can see up here, the z direction is the direction of the wave propagation. And as you look in the x direction, it's clear that nothing is changing in the x direction. So actually, interestingly, if this is an electric field, we could say that the partial of E with respect to x is equal to 0. And then it's really difficult because this is a three-dimensional vector field, but I'm trying to represent it in 3 dimensions, and you can't really do that. So the y direction is being used to represent the actual value of the function. But if we actually plotted the derivative with respect to y, it is also equal to 0. So this is not truly a representation of what this signal would look like. To do that, we'd almost have to represent it in 4 dimensions, which we can't do, obviously. So just be aware that there is only variability in one of the 3 dimensions. That's kind of what I want you to think about. One way to think about this, if you think about like throwing a pebble into a pond, you know, those rings that move away from it, that's a plane wave, or I guess it's a spherical plane wave, if you will, because it's really only moving in the rotational direction. It's only moving in the rho direction, and so it's not a plane. It's not one dimensional, but it's the closest analogy that I think that we can get that we can get to a plane wave. So we're going to see some examples of plane waves, but the thing to remember is that they only vary in one direction. And so the nice thing about being that they vary in only one direction means that we can omit x and y from the description of the function. Notice that the subscript here, the e sub y, that's representing the direction in which the wave is polarized. So it's going up and down in the y direction, but the z direction is the direction of propagation. It's the direction that will have some dependence on the function. I also wanted to mention that the distance between 2 consecutive peaks or troughs, that is known as lambda, which is the wavelength. We'll come back and talk about wavelength quite a bit later on. Now, so if we also know that the wave is time harmonic, and as you know, time harmonic means that the only time dependence is sinusoidal, then the z and t dependence can be separated. So if we can separate the z and t dependence, it makes the differential equations a lot easier to solve. So we're going to have a z dependence, which is e sub y of z, and we're going to have a time dependence, which is the cosine of omega t, but we'll represent it as e to the j omega t. So let's investigate whether and how this function satisfies the wave equation. So we're going to start out by calculating the second derivative of e sub y with respect to z. Well, if you've got, this is the z part of it right here, and this is the t part of it right here. If you're calculating a partial derivative, then the t part of it's going to remain unchanged, and the derivative is all going to be applied to the z part of it. And so that's why you can see that the z has picked up a second derivative here, but the e to the j omega t has remained unchanged. Next, we're going to calculate the second derivative with respect to time. Well, now the z part of it's going to remain unchanged, and now the time part of it is going to get a derivative. But the derivative of an exponent is the easiest derivative that there is. It's really the same function, but in this case there's a j omega multiplying the t, so the chain rule requires that we pull down a j omega and put it in front for each derivative that we're taking. We're taking 2 derivatives, so therefore we get 2 j omega terms, or j omega factors in front here. Well, now we're going to substitute those into the wave equation, and what we find is that we have the partial derivative with respect to z, And then we have the term that is the partial derivative with respect to time, although there is no, we can actually literally calculate that partial derivative. And so if we, this j squared is going to become a -1, and that -1 is going to cancel with that -1. And then this omega squared is going to move up into the numerator of this fraction right here. So this will become omega squared, and that's where we get this form of the equation right here. Now if we go one step further, and we're going to define the wave number. The wave number is k. And we're going to talk more about the physical significance of the wave number, but for right now, just be aware that we've specified that the wave number must be omega divided by c. If we do that, then this equation obviously would become, this would become k squared, and then we end up with what's called the one-dimensional Helmholtz equation. Helmholtz almost made it as the historical perspective for today. I would encourage you to look up Professor Helmholtz. But the Helmholtz equation is a well-known differential equation, and it has a well-known solution. And that is that there's an a e to the minus jkz plus b e to the jkz. So there's a negative exponent and there's a positive exponent. We're going to add the time dependence back in. When we do that, we obtain equation 19.28, and then we're going to combine the exponents together to get equation 19.29. Of course, we understand that this is going to become, ultimately, when we take the real part of this, we're going to get an a cosine of omega t minus kz, and here we're going to get a b cosine of omega t plus kz. And even though we didn't make an assumption when we were doing this derivation, we can ultimately find then that this does in fact have a rightward moving component and a leftward moving component, and they will travel at the same velocity. And we also have specified what is the condition that must be true for this plane wave to satisfy the generalized wave equation, and that condition is this one right here. That this is a necessary condition for the waves to propagate. That the wave number, which really describes the spatial variation of the wave, has to be equal to omega, which is the time variation of the wave, divided by c. So you could also think of it as like the velocity, the speed of propagation, which is provided to us, has to tie together how the spatial variation changes along with how the time variation changes. So we have a relationship here between space and time and velocity, and that must be satisfied. So this must be true. And if it is true, then this will satisfy the wave equation. If it's not true, then it won't satisfy the wave equation. So we can also say that we can also refer to c as the phase velocity. So v sub phi. Sometimes we'll just refer to this as v. We'll tend to be a little bit more precise and refer to it as v sub phi in some cases. That's either going to be plus or minus c as the wave is propagating to the right or to the left, and we know that that has to be equal to plus or minus omega over k. So we now have a lot of different quantities. We have let's see, we have the wavelength lambda, we have the wave number k, we have the radial frequency omega, the frequency f, the period t, and the phase velocity v sub phi. I put together this table, or I guess it's an image that is sort of like the circle of life for electromagnetic fields, electromagnetic waves. I've never seen this anywhere else, but I think that it's very helpful because, again, this was something that when I was a student was very confusing to me, how all of these variables related to each other. It's interesting that if you're given two of these, I guess I should specify you can't be given f and t. That wouldn't be sufficient, basically you have to be given one on the left and one on the right, something that corresponds to space and something that corresponds to time, or you can have the phase velocity. But I guess it's not fair to say that that if you know any two of the variables, let's say if you know the right two of those variables, you can find the others. You can find the other four as well, but you can, for example, you can imagine if I gave you omega and f, that would not be sufficient to find everything else. But if I gave you omega and v sub phi, then that is actually sufficient to find everything else. So let's do an example. An electric field in a vacuum is determined to be polarized in the y direction. It has a peak of 100 microvolts per meter at z equals 0, and then the very next peak is at z equals 5 centimeters. So I want to determine all those quantities and then write a complete function for e sub y of z comma t. Well, one thing that I know right away is that lambda is equal to 5 centimeters. Since the two consecutive peaks were 5 centimeters apart, that tells me that that's going to be lambda. I also know that v sub phi is going to be equal to c, which is 3 times 10 to the 8th meters per second. I know that because it says that it's in a vacuum. And the speed of light is always going to be c, 3 times 10 to the 8th meters per second in a vacuum. I can also calculate k. K is 2 pi divided by lambda, and I'm getting all of these equations from figure 19.2 here. So k is equal to 2 pi divided by lambda, which when I plug that into my calculator, I get 125.7, and the units of k are meters to the -1, although I've also seen them written, and I kind of like radians per meter, because remember that that a radian is really a non-unit. It's just it's a word that we say instead of 1, and so 1 over meter, or radians per meter, or meter to the -1. Those are all good ways to represent the units of k. We can also calculate omega. Omega is equal to k times the phase velocity, which is going to be 125.7 times 3 times 10 to the 8th, which works out to be 37.7 times 10 to the 6th radians per second. And that's not times 10 to the 6th, that's times 10 to the 9th. Sorry about that, times 10 to the 9th. And then we can have F equals omega over 2 pi, which is, it turns out, 6 times 10 to the 9th hertz, which is 6 gigahertz. And then we can calculate T is 1 over F, which is 166 times 10 to the -12th seconds, which is 166 picoseconds. So we can calculate all 6 of those quantities because we were given 2 of them. We were given implicitly we were given the speed of propagation, c, because it's in a vacuum, and we were also given the wavelength. And we can go ahead and write our equation E sub y of z comma t. Notice that it is E sub y because that is the direction of polarization, and we were told here it was polarized in the y direction. So E sub y of z comma t, and I know that it is of z comma t because I was quoted z equals 0 and z equals 5. So I know that that's the direction of propagation of the wave. So this is equal to, and it says that the peak is 100 microvolts per meter. So I'm going to start out with 100 times the cosine of, and it's going to be either, you can write it in a variety of different ways, but I'm going to write it as omega, so that's 3.77 times 10 to the 10th t minus k, which is 125.7 times z, and then it's in the a sub y direction because that is the direction of polarization, and then the units are microvolts per meter. So that's my final answer. Notice that this is the direction of polarization, and this is the direction of propagation. And this negative sign indicates that it is moving to the right, or in the positive direction. So this relationship between propagation and polarization, we're going to be talking about that a lot. So I wanted to try to highlight where that's coming from. Okay, let's talk about characteristic impedance. This is one of the most remarkable things that I think that we can discover in this class, is that there is a firm relationship between the magnitude of the electric field and the magnitude of the magnetic field. So we're going to start off by assuming that we have an electric field. We'll assume that it's polarized in the y direction. We'll assume that it's propagating in the z direction. And I can see that because, well, I can see it for 2 reasons. I can see it because there's a z here and because there's a z here. And I can furthermore see that it's moving in the positive direction, or moving to the right, because it has a negative sign. So omega t minus kz, or you could say t minus, so it's moving to the right. Let's see, what was the original form that we had there? That was z minus ct. So it's either moving to the right, it's moving to the right. Notice, although we have omitted the y subscript, we know that this wave is polarized in the y direction because of the unit vector, and we also know the wave is moving in the positive z direction because of the omega t minus kz term. Next, we're going to write Faraday's law for time harmonic plane waves. So this was, we've already talked about time harmonic plane waves. We've talked about Faraday's law. We saw that we can put them in phasor form, and this is the phasor form of that. And in particular, I'm going to use this equation right here. I'm going to use the relationship between these two. And so if I wanted to solve equation 19.32 for h, then I'm going to have a minus 1 over j omega mu sub 0 times the curl of E. Well, I know the function of E. Function of E is given in equation 19.31. So I can take the curl of E. Notice that this constant here, this constant becomes this constant right here. So that's the same. And this is simply, this determinant is the curl of E. Well, I can use the method of diagonals that we talked about way back in, I believe, in chapter 2 to talk, or maybe even, yeah, it was chapter 2, I believe, to talk about the method of diagonals. And essentially there's only one term out of all the terms that we can get here. Out of the 6 terms, only one of them is going to be positive. And so here you can see this is the one term that turns out to be positive. When we take the derivative of this term right here, then we end up with an extra negative j times k, because there's a j here and there's a negative k here. So when we take the derivative with respect to z, the chain rule pulls those out in front. Well, let's see a few things. The j's are going to cancel, and 2 of the 3 negative signs are going to cancel, but we're still going to keep 1 extra negative sign around. And so this term gives us the form of h. Remember that if I scroll back up again, remember that E was in the positive a sub y direction, and if I scroll back down now, h is in the negative a sub x direction. So we can note then that the direction of motion is let's see, the direction of wave propagation, which we will now call a sub k. So remember that this is I'll call this the direction of hold on a second. It's the direction of wave propagation, a sub k. And we already identified, if I scroll back up again, we already identified that it was moving in the positive z direction. So right away from the very first line, we could say a sub k is in the z direction. It's moving in the positive z direction. So we now know the direction of polarization of E, the direction of polarization of H, and we also know the direction of propagation. And let's look at those on this graph here, on this figure. E is in the positive y direction, H is in the negative x direction. Notice that over here is positive x, but H is in the negative x direction. And at first that might have seemed like it would have ended up being a mistake, but if you put your finger in the direction, if you put your hand in the direction of E, and then you curl it into the direction of H, which is pretty easy to do here, so we're just curling it into the direction of H, your thumb is going to point along the positive z direction. And so that's going to give us S, because remember that S is equal to E cross H. So we can calculate the direction of S, and as it turns out, the direction of S and the direction of K are both in the a sub z direction. And this will always be true, that the direction of S and the direction of K will always be equal to each other, because the direction of K is the direction that the wave is propagating, and the direction of S is the direction that energy is flowing. So it's very intuitive after we see it, of course, that yes, of course, a sub S must be equal to a sub K, which in this one example case is equal to a sub z. But that's not always going to be true. This is always going to be true, that a sub S is equal to a sub K, because the direction of propagation is necessarily the direction of power flow. Now, we can talk a little bit about the relationships among the directions. That's what we've sort of understood. But now we can also talk about the relationships among their magnitudes. Let's say that we were given the magnitude of E. If I scroll way back up to the beginning of this section, we were given that the magnitude of E is equal to A. So the magnitude of E is equal to lowercase a. What I'd like to know, is there a relationship? Notice here is the magnitude. Oh, not with the negative sign. Negative signs don't go to the magnitude. Here is the magnitude of H. Is there a relationship between the magnitude of E and the magnitude of H? Let's see what happens if we take the ratio between those two. Well, one interesting thing that happens is we see that the ratio is going to be volts per meter divided by amps per meter. The meters are going to cancel. We're left with volts per amp, and that's units of ohms. So that's kind of a quirky thing, is that the E divided by H will always be in units of ohms. Well, we can take the magnitudes. Well, the e to the j omega t minus kz's are going to cancel, and the a's are also going to cancel. So we're left with 1 over the quantity k over omega mu sub 0. Flip the denominator and it becomes the numerator. We have omega times mu sub 0 over k. We feel pretty good about that result. That's a very valuable result, and we could probably use it for a number of different cases, but we can do one step better. We're going to plug in the fact that omega is equal to kc, and then we're going to cancel the k's, and this becomes c times mu sub 0. Those are two physical quantities. It would seem like that's a pretty good place to stop, but we can go one step further, because remember that c is equal to 1 over the square root of mu sub 0 times epsilon 0. Cancel half of this one, so this will become to the 1/2 with the denominator, and we're left with the square root of mu sub 0 over epsilon 0. Let me just remind you that we know that c is equal to 1 over the square root of mu sub 0 epsilon 0, and now we've just discovered that z sub c is the square root of their ratio, of their quotient. So we've got some pretty interesting results here, and those two physical quantities seem to be universal. And in particular, if we're talking about free space, which we are here, we can give that the subscript 0, and we'll call that the impedance of free space, the characteristic impedance of free space. We plug in the actual numbers, and we get 377 ohms. Now, I know that in a lot of times in this class, I'm the person who is the cheerleader for whatever this important result was, and I'd say, try to just recognize the splendor and magnificence of this result, and it is so incredibly significant. And now I'm going to kind of go the other way, and I'm going to say 377, that's just a number. You will never be able to go out and like hold a multimeter up to the sky and measure 377 ohms. It's a ratio, and it's an incredibly useful result, but don't try to read more into it than there is. This isn't like the answer to the universe. It's 377 ohms. It's a valuable result, but I don't know that it goes deeper than being a valuable result. So we know that the magnitude of the electric field will always be 377 times larger than the magnitude of the magnetic field when everybody's using SI units. So we can combine our understanding of the relationship between the magnitude. So here you can see this is going to deal with the magnitude, and then this one's going to deal with the direction. So we know that the direction of H is equal to the direction of K crossed with the direction of E. You know, you can actually you can do an axis plot here, and we know that let's just imagine that this one is E, so this would be A sub E, and let's call this A sub H, and then we can use the pointing vector to go from E curl to H, and then our thumb is going to point in this direction. So this is A sub K, which is also A sub S. So if I wanted to say what is A sub K crossed with A sub E, so I'm putting my fingers in the direction of A sub K, curling them toward A sub E, and then in fact I do get A sub H, so this equation is in fact valid. And so that's really how we're putting in the relationship here. Similarly, if I told you the direction of H and the direction of K, you could use that to derive the direction of E as well. So this equation is specialized, it's customized for going from E to H, but I could also give you H and ask you for E, and you could do that as well. So here we have a function for an electric field in a vacuum. We want to find the direction of wave propagation, and we want to determine a complete expression for the magnetic field that corresponds to this electric field. Okay, so first of all, let's look here. I can see that it is polarized in the y direction. So this is polarized in the y direction. But that's not the same thing as the direction of propagation. The direction of propagation is going to be according to the z variable here. And so propagation, and this is a negative sign, so taking those two together, we find that this is in the positive z direction. So I can immediately, just by inspection, write A sub k equals positive A sub z. So I can see that the wave is propagating toward the right just by inspecting the term that's in parentheses there. Okay, so I know that H sub y, oh, and I should mention that I know that, oh, it's not H sub y, it's going to end up being H sub x. Well, I'll just omit the subscript because I don't really know that yet. So this is H of z comma t. And I do know that the direction of propagation of E is in the positive z direction, then the direction of propagation of H is also in the same direction. that the E and the H waves are always going to be linked together. They will always be in phase, they will always be at the same frequency, and they will always be propagating in the same direction. So this is 1 divided by Z sub 0 times A sub k crossed with E of Z comma t. So this is 1 over 377 times A sub z, and we just saw that A sub k was equal to A sub z, crossed with 100, and that cosine, we can leave it in cosine form, we could convert it into a complex exponential. Just for simplicity, I'm going to leave it in the cosine form. This is, and I can leave the 2 pi separated out for now. This is 10 to the 9th t minus 40z, and that was in the A sub y direction, and it was millivolts per meter. And if I now take the magnitude of the electric field, which was 100, divided by 377. So this is going to be 100, and I'm going to include the milli times 10 to the negative third divided by 377. I can see that I'm still going to keep the cosine of 2 pi times 10 to the 9th t minus 40z. That part will always remain the same for the electric and magnetic fields. Those are always going to be equal to each other, and so we can always leave them unchanged. And then it's going to be A sub z crossed with A sub a. Now when I'm faced with that cross product, I have 2 choices. I can either look it up or I can figure it out. Whoops, I don't want to do that, whatever that was. I'm always in favor of, I want to be able to figure this out if I find myself stranded on a desert island. So let me plot, I'll put it this way. So here is A sub x, and then this is A sub y, and if I curl x into y, I do remember that that's in the A sub z direction. So the only one that I need to remember is that A sub x crossed with A sub y is equal to A sub z. So now if I put my fingers in the direction of A sub z and curl them in the direction of A sub y, so I start out by pointing them in this direction, and then they end up by pointing in this direction, and my thumb points in this direction. And so that's in the negative A sub x direction. So that means that this is negative A sub x. So that means that this is, and that ratio was 265, so 265, and I do need a negative sign. Negative 265 cosine of 2 pi times 10 to the 9th t minus 40z times A sub x, and those units are going to be microamps per meter. And so that's my final answer. So just by given E, I can tell you the direction of propagation, I can tell you the magnitude and direction of the magnetic field. It's really interesting how you can find out so much information just being given one thing. So now we understand that both the electric field and the magnetic field vary sinusoidally in both space and time for a plane wave. They are perpendicular to each other, and the direction of propagation is perpendicular to both of them. We refer to this combination as an electromagnetic wave. So when we talk about electromagnetic waves, it always means that there's an electrical component perpendicular to a magnetic component, and that the direction of propagation is perpendicular to both of them. Neither wave would persist without the other, and propagation is only possible when both waves are present at the same frequency and in phase with one another. So here you can see that I have an image that sort of represents that. You can see that the electric field is polarized in the y direction, the magnetic field is polarized in the z direction, and the direction of propagation is in the x direction. So I think that this image, as you're thinking about electromagnetic waves, I think that having a picture like this in your head is extremely helpful. Last thing for today is to talk about power flow. And we've already seen that the direction of the Poynting vector, the direction of power flow, is going to be in the same direction as propagation, but we can actually calculate actual power flow now. We actually have enough information to calculate this power flow. Remember that we had an equation 18.28, which was to calculate the Poynting vector. If we take the surface integral of the Poynting vector given a particular surface, if I have a Poynting vector that's pointing this way, and you could kind of think of it as the Poynting vector is pointing that way a variety of times, and if I have a surface that's passing through it, well, that's going to give me the total power. So the S vector at each point is pointing in a particular direction, and they may not all point in the same direction. Typically they will, but not necessarily. And whatever portion of that is captured by a particular surface area, that's the portion that's going to be included in the power calculation. So it turns out that if we have the knowledge necessary to calculate h of z from e of z, then we can perform this calculation for the Poynting vector given just e of z and the propagation, the direction of propagation. So if we're given e and if we're given the direction of propagation, from that we can calculate h, and from e and h we can calculate s. So what we want to do is we want to calculate those things. Interestingly, we don't even need to know the value of the wave number, the wavelength, the frequency, the period. All of that's going to cancel out. All we really need to know is actually just the magnitude of E. So given the magnitude of E, we can calculate the magnitude of H, and from that we can calculate the S. So we can calculate the magnetic field from the electric field. Here you can see that it's polarized in the x direction. But when I look at this, and this won't always be the case, today I've made them, every example is propagating in the positive z direction, but that isn't necessarily going to be the case in all of our examples. So I know that a sub k is equal to positive a sub z. I can write h of z comma t is equal to 1 over z sub 0 times a sub k crossed with e of z comma t, and that's equal to, I have it's 25 volts per meter. So 25, I'm going to erase this just so that it's not quite so constraining. This is 25 divided by 377 times the cosine of omega t minus kz, and that's going to be times a sub z crossed with a sub x, and it turns out that a sub z crossed with a sub x is a sub y. Let me just go back up and double check that. I had written an axis earlier. A sub z crossed with a sub x, yes, that does in fact give me a sub y. So I'm feeling good about that. So now I can, yes, I can check that, yes, when I do this curl, so let's say check, I get E cross H is going to be equal to A sub X cross A sub Y, and that is A sub Z, which in fact is equal to A sub K. So I'm feeling good that A sub S is pointing in the same direction as A sub K. So let's calculate the average Poynting vector, and remember that anytime that you're working with sinusoids, the average is going to be over at least one cycle, so that's where the 1/2 comes from. 1/2 times the real part of 25, and now I am going to put them into complex exponential form for a reason that's about to become very clear. Omega t minus kz, and then that's going to be multiplied by, oh, and I forgot to say this right here is 0.0663. So that's times 0.0663, and then don't forget that Poynting vector has to have h has to have an asterisk. So if I come back up here, notice that this asterisk means that it's the complex conjugate. And the complex conjugate simply means that whatever the imaginary part is going to become negative. Well, in this case, that means that this is going to become e to the negative j times omega t minus kz. And this e to the j omega t minus kz will cancel with this e to the negative j omega t minus kz. And I'm left with, oh, and the direction of the vector was a sub x crossed with a sub y. And so when I multiply this out, I get 1.658 a sub z, and the units of the Poynting vector are watts per meter squared. And then to calculate the average power, notice that I want the average power through a circular opening centered at the origin with z equals 0 and a radius of 2 meters. So the average power is actually going to be quite easy to calculate. This is a double integral of the average Poynting vector over a surface area, which is going to be rho d phi. So this is going to be from rho equals 0 up to 2 and phi equals 0 up to 2 pi, but the average Poynting vector is a constant. I should say there's also an a sub z here on the end. So the a sub z dotted with the a sub z from the average Poynting vector is going to go away. I'm left with 1.658 times rho squared over 2 evaluated between 0 and 2, and phi evaluated between 0 and 2 pi, which when I do all of that calculation, punch it all into my calculator, I get 20.84 watts. So how much energy, how much power is flowing through that circle? As we see, power is flowing through the circle in the quantity of about 20.84 watts. So we've covered a lot of ground today. We've done a lot of good stuff. We proved the general form of a solution to the wave equation. We proved that that a plane wave, will depend only on one variable, and that variable will be the direction of wave propagation. It's different than the direction of wave polarization. We saw that time harmonic plane waves are a solution to the wave equation, but only if there's a relationship between c, omega, and k that is followed. We saw that the solution to the time harmonic, the solution to the wave equation, that is the time harmonic plane wave, will have a form that looks like this. We saw that if we know two of the values, let me try. If we know the right two of the values, so they can't all be associated with space and they can't all be associated with time, then we can find all of the others. The direction of wave propagation is always the same as the direction of the Poynting vector, which is E cross H. The ratio of the magnitudes of E and H can be found according to that calculation, which is 377 ohms. Always going to be 377 ohms for free space. And then given an expression for E, we can then calculate H, and given E and H, we can calculate the average power flow.